I've listed the EMF, the shape and dimensions, the cross-sectional wire, the length and current. So what it, again, oh, there we go, first sentence, an ideal battery, no internal resistance. That's why I'm justifying EMF. I could have easily just said voltage as well. So the ranking resistivities. Well, what's a formula which has resistivity in it?
What's the formula that has what in it?
Is it
Resistivity.
Oh.
is it the rho L over area
It is what?
is equal to the resistance?
Okay.
That symbol's called rho?
Rho.
Oh, okay. Ah.
Greek letter. So rho is just the resistance times the area over the length. And what I gave you here was,
Isn't Ra the name of the symbol?
not ideal wiring circuit, let's do that.
Today has been a weird day.
Oh, I gave you current. So resistance, from Ohm's law, I know that delta V is equal to IR. So R is delta V over I. So this is equal to delta V A over IL.
Changing Virginia over Illinois.
And this is my EMF. Current is given, length is given, and then enough information to figure out the area is given. So let's at least go through one of them. The first one is the cross-sectional of a circle. What's the area of a circle?
R squared.
And I give you a diameter of x, so you can also write this as 1/4 pi diameter squared, or just divide the diameter by 2 and then square it. So my resistivity for A is my voltage, E, times my area, which is pi x squared over 4, times my current of 2I, times my length of L. So I get pi over 8, then EX squared over IL. And I would expect that that's going to show up again and again, so you're basically comparing this, the coefficient. So that would be A, B. Let's see, so my voltage is 2E. It's a square, and I give you the dimensions of that square, so my area is going to be 2x squared, divided by the current of I and a length of 0.5 L. And lo and behold, we have the EX squared over IL, and then the number in front is 8.
What is E?
E on here, E is, I give you the EMF in terms of some constant E. The E, for those who go into electrical engineering, EMF should be an epsilon, either that or that.
Okay.
When you first started printing, printers did not necessarily have the Greek letters. So what a number of printers did is they used the capital E.
But that.
Electrical engineering textbooks, unless this has changed, will use capital E for the EMF as opposed to an epsilon.
Do they still talk about electric fields and stuff like that?
Yeah,
Is that a
oh yeah.
different symbol? Wait, will
or
I-
electric field.
Oh, it's a vector. Will I have the?
So physics textbooks will either do that or that. And again, engineering textbooks, I believe, probably still use this. So if you happen to run across E equals IR, that's
Okay.
Ohm's law.
Weird.
That's what I find so
It does.
strange. It's like across all the fields, you guys don't have a consistent set of variables or letters.
Yeah, that would require one group going, okay, we'll start using what you're using. We will abandon 200 years worth of our notation. A lot of egos involved. Again, get the position of power.
So all we have to do is
Oh,
write a
well,
text.
And I can use my ego.
If you wrote a textbook at a, probably MIT, Harvard, Princeton, Yale, one of those, MIT probably be your best bet.
You don't wanna write the textbook, you don't need the editor of all
sorry to say.
textbooks.
I'm thinking.
So then you get the final say.
We
So
need
why
to
would,
go to MIT now.
why would an engineering department adopt a textbook if it has all the weird notation?
Cause it has the
Don't
weird
tell
notation.
them.
But I bet it's got something to do
All right.
with how they do it.
So there's some things to iron out here.
Okay.
And so on. Yeah, it's just a matter of plug and chug and then comparing those. And don't make a careless error. It's as simple as that. Is there a need for me to finish going through 3?
I don't think so.
If you change your mind, you know where to see me, right here.
Anytime.
I'm not here anytime. But it just seemed to be brought back by popular demand. Or demand. Whether popular or not.
Unpopular demand.
Hey, still brings me back. All right. Any questions about, now that I've erased most of what we've done, any questions about problems 1 through 3?
Also, these are ours to keep, correct?
These are
Like, these are ours to keep?
Oh, yeah.
Okay, great.
souvenir of your visit. Stop telling people I never give you anything. All right, so now we get into some circuit analysis here, some good stuff. I got some voltage here, which presumably will be named later. I've got 2 ohm resistor, 5 ohm resistor, 3 ohm resistor, 1 ohm, 6 ohm.
Those are omega, right? Those symbols are omega?
Yes, they are omegas, capital omegas. Lowercase omega looks like a W.
It must have been so cool to be writing in Greece.
It's very average. I can confirm.
You can confirm?
I can't confirm.
All right. So the first question is, what's the equivalent resistance? So this is just a matter of working it out, series, parallel. What do we add first?
Do we, are the 5 ohm and the 6 ohm, are those the only ones that are parallel?
I would contend that they're not really parallel.
Do we treat them as parallel for the sake of the problem?
Not yet.
Are 2 and 3 parallel?
Not really.
They're not going anywhere, just going to one.
All right. Figure out where the junctions are.
Alright.
Do I have, going from one junction to the other, is there any place where I'm going to pass by 2 resistors?
Yes.
Which path?
Either of them,
1 ohm and the 6
the
ohm?
left or the right.
Well, there's a battery in here, but, yeah, I have to add those first before I do the parallel.
And then that's parallel with the 5 ohm resistor?
Yes.
Okay,
That
great.
is. You have to do the series first. Don't do 6 and 5 in parallel yet, because that 1 ohm is messing it up. So that is a 7 ohm resistor, so I've still got that, I got my 2 here, my 5 there, my 3 there, and now I've got 7 there. Now I got a parallel. These two are in parallel. The resistor of 156, and this is just my notation for the resistors that I'm combining. This would be R16, this is R5, R3, R2. Which I think is how I have it labeled on here.
Yeah, 2.916 ohms repeating.
Well, I know it's gotta be less than 5. If I'm adding the parallel, my equivalent resistance has gotta be less than any of my individual ones. Also, if they're the same, it would be cut in half, so I got 1/5 plus 1/7. If they're 1/5 and 1/5, I'd have 2.5. And so, ballpark seems reasonable. So I've now broken this down into 2.916 repeating, and 3. Now what?
Just add them all together.
Adam.
Yep. That's a series there, because current flowing across the first, this one has to flow across that, has to flow across that. There's no junctions, nothing taking it a different path. So we end up with my equivalent resistance, 7.916 repeating ohms.
Nice.
And you can pretty much be sure there's gonna be some problem where you have to find an equivalent resistance and equivalent capacitance. All right. Questions on this?
Capacitance formulas are just the opposite of resistance.
Yeah. You'd still do it in the same order, just different formula every time you combine them. And that's part, yeah, part D is, I say, hey, pretend that they're all capacitors with units of farads instead of ohms. All right, so the next one is R2 is a light bulb. And the incandescent light bulb is just a resistor. You run current through it, there's enough resistance, it heats up, it glows, we see a light. It's incredibly inefficient because most of the light that's given off is not in the visible spectrum.
Oh, nice.
What? Wait, hold on.
I did not know that.
For the incandescent lights, the filaments,
Okay, but like LEDs are different?
yeah,
Okay.
Are LEDs better?
definitely more efficient.
Huh.
Crazy.
Are they still making like new kind of tech for that? Like making more and more efficient lights?
Yeah,
I hope so.
they are, at least in the commercial and industrial settings. They're always upgrading the T8s to like T4s, T12s.
Okay.
Yeah, they're slowly switching them over from the incandescent to LEDs, but it's coming.
I have a question. If you can't, what kind of light is it if it's not visible light for the incandescent bulb?
Light is a generic term for electromagnetic radiation.
Yeah.
So visible light is within a narrow spectrum of wavelength. If you, infrared, microwave,
Okay.
X-ray?
yeah,
Gamma
And all of
rays.
them give off electromagnetic radiation?
those are all forms of electromagnetic radiation.
Okay.
So from a physics point of view, the math behind them is all the same, it's just a matter of it's a different frequency, but
And just to
the rules
clarify,
obey.
what exactly is radiation? Because you say radiation, I think of like, you know, like a nuke.
There's basically 3 types of radiation, alpha, beta, and gamma.
Okay.
Middle of chemistry.
All right, so beta radiation. So they came up with the names of alpha, beta, and gamma radiation before they really knew what it was, but beta radiation turns out to be electrons just being shot. Alpha radiation turns out to be helium nucleus,
Oh, okay.
and gamma radiation turns out to be electromagnetic wave.
So gamma's what, like our light star and stuff?
The, what,
Is gamma like the most common one?
no, I mean.
Everything we see
It depends
is-
on what's glowing.
It's the most penetrating one.
But not,
Now, and this is where, basically where it started. Gamma radiation is a specific wavelength at this point, but really, any electromagnetic wave can be considered radiation.
oh, okay.
The dangerous radiation is what's called ionizing radiation.
Oh.
If because if I have an atom here, and I got electrons zipping around wherever it happens to be,
Yeah.
as radiation comes in, it could potentially hit an electron and send the electron off. Because of conservation of energy, the radiation that comes out is less than it was. Stay. This is known as Compton scattering,
Okay.
and this is a place where you can, it's a question of whether light's a particle or a wave. If you treat it like a particle, the math works out really beautifully. So anyway, if you send an electron off, we now have an ion here. This ion can start to connect to any other ions that are floating out there or potentially polarized. But radiation that causes ions to be formed can suddenly start changing DNA. I mean,
Okay.
the fact that basically it causes something else to be formed
Okay.
instead of what's intended to be.
Because it's like bonding to whatever it can essentially,
Yeah.
and thus it'll change whatever it's connected to.
Now, most of the times that we get radiation that suddenly creates something new, it's not viable and that dies. That cell or whatever it is dies. So that's just part of life, and
Right.
there's no danger there because it can't replicate.
Oh, okay.
Some of the formed cells or the radiated cells are cancerous and will grow very quickly. Yeah.
So, that's what happens when when Hiroshima happened and people were in the hospital. They all, like a lot of people just got cancer within a week
Yeah.
of that.
As well as most of the crew from the movie,
True.
the John Wayne film, he played Genghis Khan. I'm blanking on the name of the film, but it was filmed out in the desert near where they did the nuclear testing. And so a large number of those people ended up with cancer.
That's crazy.
What?
Even 50 years after, or I'm not saying 50, like 30 years after or whatever.
Yeah. Yeah.
So it lingers for a while then, huh?
It depends on, what got affected, what cells. I mean, there are some what are called the aggressive cancers that, it hits that and it's a confluence of horrible events there where suddenly it grows very quickly. And then others where it has to incubate and then grows slowly until it takes off.
I feel like if I knew as much as you, I would be afraid of life.
Yeah, there's,
You know the physics behind like some of the worst stuff that could ever happen to you.
there's a professor, was a professor too, I suspect he's gone now, but, Ernie Elsevier, who was a fighter pilot for the Dutch Air Force during World War II, or had been. And so as a pilot, he knew all the things that go wrong with a plane, and then he became a mechanical engineer. So he knew all the things that could go wrong with a plane. So he had this incredible fear of flying, despite having been a pilot. And though he can't get away with this now, fortunately, but the way that he would deal with it is he would get drunk before taking a flight.
What?
I mean, if it's an effective solution.
You know what? It works. One time my uncle got
It's possible he's an alcoholic too. I don't know.
One time my uncle got into like a fatal car. It should have been a fatal car crash. Like he was going like 140 in a Cura, which is made out of freaking aluminum, and he went off of a rail, hit a tree. But because he was so drunk, he woke up in the hospital hungover, not a single injury.
So if you're gonna do dumb stuff, get cranked.
Essentially.
Yeah, there was basically dad's second wife's, one of her sons, was drunk and skiing and ran into a pole, a pier pole. And the line of, well, it's a good thing he was drunk so that he was loose. I don't know if the person who said that also thought, well, if he hadn't been drunk though, he wouldn't have hit that. This sounds like a good place actually to, let's take a break, stretch legs, get focused on physics.
Get quiet.
If you are afraid of physics, don't get drunk. Alright,
It's not that far.
For the airport.
you're rolling.
Yeah, well before the airport.
Alright, the next part of this is that if R2 is a light bulb, what is the voltage, what's the maximum voltage we can have before the light bulb blows? And we have it in here that it will blow if the current gets above 2.4 amperes. So 2.4 amperes, whichever way the current's flowing, 2.4 amperes, let's go put it that way, is the maximum, I max. And what I'm trying to figure out is my maximum voltage.
Do you multiply that by the total resistance or just by the resistance of the light bulb?
The resistance of the light bulb would just tell you the change in potential across just that resistor.
Okay, so it's the total?
Yeah, so in this case right here, because the current flowing across here is the same as the current flowing out of here, if all I need to do is figure out the current flowing out of the battery.
Is that
All
light
right,
bulb?
I'm sorry, I need to know what the voltage that will produce 2.4 amps coming out.
Is that light bulb, it takes over the resistor, so the 2 ohm resistor is gone? Or is it
Well,
still
it's
there?
still a 2 ohm resistor, it just
Okay.
happens to be, it'll glow.
It'll glow.
And I have not done any of these experiments, as an instructor, but it used to be that if you needed, a bunch of the same resistor, you could just go buy some light bulbs.
Now, would it be wrong just to take our 7.916 and just times that by 2.4 to find volts?
Not only is it not wrong, it is the correct way of going about it.
Oh,
What?
that's what I was thinking, though.
All right, so I know that delta V is equal to IR.
Okay.
I know that, this is what I'm trying to figure out. The current across here can't be bigger than 2.4 amps, and therefore the current coming out of here also cannot be bigger than 2.4 amps, because it's the same current. There's nothing in between that would cause the current to veer off.